All right, this is video 9.5. Today we're doing the fundamental counting principle. Now it's pretty wordy, but it's really not as hard as it sounds. If you have two items to choose, and let's say there are m ways to choose the first item and n ways to choose the second item, then the number of ways altogether that you compare them would be m times n. So for example, let's say you had 5 shirts that you took on vacation, and you had 4 pairs of shorts, and they all mix and match very nicely. So what different combinations do you have? Well, you would do that 5 times that 4 and say there are 20 total possible outfits you could make from your 5 shirts and your 4 shorts. So let's use our fundamental counting principle and talk about passwords. So a lot of programs will use these for computer-generated passwords that people can use to get on a secure network. My husband has one for his job. It's called a VPN, and so it gives him an automatic password that is regularly changed so that you can't break into the company's programs without having this VPN password that is randomly generated. So let's say that this computer randomly generates a 5-character password. The first 2 are going to be letters, and then the last 3 are going to be digits. And so all the passwords are equally likely. So let's find the number of passwords. So the way we would do that is our first thing is going to be a letter. Well, how many different options do you have to have a letter, right? There's 26 letters in the alphabet. So our first option, there are 26 different ways to pick the first character. Second character is also a letter, so that would be 26. And the third character is a number. So it's anywhere from 0 to 9. So then that's 10 digits, and then another 10, and then another 10 digits. So the way to find how many passwords there are, we're going to do 26 times 26 times 10 times 10 times 10. And we would get 676,000 different passwords, which makes it very difficult to crack because nobody's got time to type in that many random combinations of letters and numbers. So let's find the probability of being assigned the password MQ836. Well, that is the only order that that password could come in. So the probability of that is going to be 1 in 676,000. Or if we take that as a decimal, we would say 1 divided by 676,000, and we would get 0.000014. That's pretty unlikely that you would get that particular password. Let's find the probability of the password that does not contain the letter A. So when we're doing that, now our first character here, it doesn't have 26 possibilities. It only has 25 because A is not included. The second one is also 25, and then the ones after that would still be 10, 10, and 10. So we'll do 25 times 25 times 10 times 10 times 10, and we would get 625,000 possibilities. So let's say we're still using the same computer generated. Let's find the probability that a password contains exactly 1 4. Now remember that there's 3 different places that a 4 can occur, and it's not necessarily, it doesn't say that it has to be the first digit or the second digit or the third digit. So you could have, you know, a letter, and then you could have a 4 here with a number. Or you could have a letter, number, 4, number. Or you could have a letter, number, 4. So there's 3 different ways that we could calculate that. So what we're going to do is we're going to find the probability that it happens in the first spot. We'll find it where it happens in the second spot, and we'll find it where it happens in the third spot. When we add those probabilities up, we'll say that the password contains exactly 1 4. All right, so if we're doing that, let's go to our 26 possibilities for our first character, our 26 possibilities for our second character. There's only 1 possibility for our first character on this one, and then 10, and then 10. So the possibility of that would be 26 times 26 times 10 times 10, and then times the 1. We don't need to put that in there at all. That would be 67,600. So if we have our 26 times 26 times 10 times 1 times 10, that's going to give us the same number. And then our 26 times 26 times 10 times 10 times 1 would also give us the same number. So I'm going to take these three and add them up. So the possibility of getting exactly 1/4 is going to add those up. Now remember, that's over our 676,000. So what I'm going to do, put this right here. I'll have my 202,800. That's the chances of having 1/4. We're going to put that over our total number of chances. So I'll divide that by 676,000. Our chances, our probability of getting 1/4 is 0.3 or 30%. Right, the other way you can do this is using its tree diagram. All right, so let's say we're packing 2 pairs of pants, 3 shirts, and 2 sweaters for a vacation. So we're going to describe all the outfits you can make that consist of 1 pair of pants, 1 shirt, and 1 sweater. So a tree diagram is where you write them out. So let's say we have our pair of pants here, and they're black. And then we have our pair of pants here, and they're green. All right, so we could pair our black pants with our 3 shirts. Let's say this shirt is red, and this shirt is blue, and this shirt is, whoop, that's a really bad shirt, yellow. Right, so we would pair our green with the same 3 shirts. Rather than drawing the shirts, I'm going to say red, blue, and yellow. And then we can also combine each of those with 2 different types of sweaters. So we might have a gray sweater, and maybe we have a white sweater. So we can do a gray, and we can do a white, and we can do a gray, and we can do a white. And then each of these also goes to a gray and white. So we could circle any branch of this tree to describe an outfit. So you could wear black pants with a red shirt and a gray sweater, or black pants and a red shirt and a white sweater, or black pants and a blue shirt and a gray sweater, or black pants and blue shirt and a white sweater, or black pants and yellow shirt with a gray sweater, black pants with a yellow shirt and a white sweater. And then all the same for the green. All right, so then that would be the description. So like this would be a description of one of the outfits. So a tree diagram also works if you've got plenty of time and you like to draw little pictures, or you can, they're not so complicated. So like the letter password thing, that one's really complicated. You wouldn't use a tree diagram on that. But I just want to show you that you've got this outfit, which is 1, 2, 3, 4, 5, 6. So we have 6 outfits with the black pants, which means we have 6 outfits with the green pants. Together, those are 12. Let's just see if our counting principle works. If we have 2 pairs of pants times 3 shirts times 2 sweaters, that's 2 times 3 times 2, which is 12. See how those numbers match up? So they both work. That's how many outfits you could have. Go ahead and click on the link and do your homework, and I'll see you when you get to class.